there, yeah.
Around your eyes.
I thought it was milk.
Yeah, what is it?
I thought it was milk.
What did I see that? Wasn't that like how they teach?
I swear I've seen it.
Yeah.
Yeah.
Maybe peons are like a jellyfish.
Okay. So this is where I think this gets a little bit tricky. It's a lot of like understanding the wording of everything. So in terms of this, they give us a function. So the temperature of an object set to cool on a counter X minutes after. So this is the temperature is going down. So it's cooling here. This is the temp. So what would the first derivative do you think that would mean? So like think about height versus time and speed. What do you think the first derivative would mean in this situation where object is cooling on the counter?
How fast it's cooling.
How fast it's cooling, so like a rate of cooling. Or like, yeah.
Oh, no, it makes sense because it asks to say cool.
Oh gosh. And then the second derivative is like the acceleration of the cooling. So it's basically how much the rate of cooling is changing. So watch out for those words like the word changing. Like that's usually a clue that, that's probably some form of a derivative. So look at these two questions and try to determine which one you think is the first derivative and which you think is the second derivative. Can you tell?
The second one is the first.
Yeah, so how fast the temperature is changing. So this is the temperature. Temperature changing then would be the first derivative. And then the rate of cooling is changing. That would be the second derivative. Now this one is a tough equation, so they give us the equations. So it's just a matter of seeing where I have to substitute it in. So I wouldn't ask you guys to find the derivative of an equation like that. However, at the same time, like it's not completely impossible, it just is, it's a bigger pain. But so we're putting 2 in for each of these, but we have to make sure we put them into the right places. So this one, the 2 is going into the second derivative. And Cash, you'll see in a second how we figure out the second derivative by hand. It's not too bad. I got like 8.12. And I guess I would probably say it's probably like degrees, I'm assuming, per minute squared. You didn't get that?
I don't know.
Can I borrow somebody?
Yeah.
Becca, do you want to come into Mr. Hatfield's room?
Am I gonna get like yelled at or something? Oh dear God, good morning.
Yeah.
And then you get like a negative 14.6 here.
Yeah.
So it's going down 14 degrees. Oh, that shouldn't be minutes squared. It should just be per minute.
Now it's down by 4 points, and I literally launched this guy like so far across the map.
All right, last one. We'll finish up here. All right. So this is our position versus time graph.
I was so confused. Like,
And then acceleration is double prime. And so again, Cash, this is what, can you jump to the back side with us so we can see how to do these two. That's what. So velocity is the first derivative. So I drop this in front, and what happens then in front there? You multiply, so what happens with the 3's? It cancels. So this is 2t to the second, right? Minus 16t plus 5. So a more complicated velocity function than we've seen before. Now the second derivative is acceleration. So again, just so you guys caught on here, this is the same thing, we just do the derivative again. So it says at t equals 60, is the object speeding up or slowing down? How do you guys think we would have to figure that out?
The acceleration.
You put because if acceleration is negative, then it should be. So then we could put 60 in there. You could check it in the velocity as well. If that was negative, that would also give us, but I believe at that point it's going to be speeding up. This is a positive acceleration. We're actually at the start. If you started at time is 0 or time is 1, 2, it's going to actually be slowing down in the beginning. So this one actually ends up speeding up. But, all right, let me get you guys a worksheet to go with this.
Can I go to the bathroom?
Yes.